much. In this video, we will see analysis of beam using ANSYS APDL. So this is the beam which we have to analyze. As you can see, the beam is fixed from one end and it is roller supported from the other end. And at a specific point, at some distance from the fixed point, it is loaded with a load of 20 kilonewton in negative y direction, and the dimensions of the beam are provided to you. First of all, we will discretize this based on the application of load. We have discretized this beam element into three nodes. So node number one, which is fixed, node number two, where you are applying the force, and node number three, where you have a different boundary condition, that is a roller support. So these are three nodes we are getting. Since there are three nodes, there are two elements, one element between node number one, node number two, and the other element between node number two and node number three. And the material property of the entire beam is given as E is equal to 200 GPa, which is your Young's modulus, 200 10⁹ Newton per meter square. And instead of giving the area, as this is a beam element, the moment of inertia of the beam is given to you, that is 24 10⁻⁻⁶ meter raised to 4. So this is your moment of inertia for a beam element. Mostly every time the moment of inertia is given to you. So using this moment of inertia, we can select one cross section of the beam, and based on that selected cross section, we will find out the values of width and height. So as here the cross section of the beam is not directly given, we will be assuming a square cross section of the beam. If it is not given, you can assume anything, right? So we have considered a square cross section, and by using the formula for moment of inertia of a square, that is b raised to 4 by 12 or h raised to 4 by 12, we can easily get the value of E and H directly by calculating as 24 into 10⁻⁻⁶ into 12. Both root of that will give you E, and that comes out to be 0.13 meters. That comes out to be 0.13 meters, right? So this is all about the specification of the question which is given. We need to sketch this, or we need to draw this or create this in ANSYS APDL, apply the boundary condition, apply the forces, and then solve to get the results what we have got using analytical calculation, normal analytical calculation. So first of all, we have to go to our mechanical APDL launcher. Once it gets launched, you need to set the directory. Once it gets launched, you need to see, this is your page where all the properties are given. This is your name of the simulation element and the license, that is academic license, which is available with us. You need to set the working directory. Somewhere on your desktop you can create the folder with your name and set that as the directory, and write the name of the job, the analysis what you are doing, and you can write. Now I am writing analysis of, and then I will press on the run button. Then this will directly take you to ANSYS APDL, right? So this is the interface of your ANSYS APDL. We can work with the black screen. If at all you want to change the black screen to white, we can go to the style, color, and reverse view. You will get a white screen, so that it becomes easier for you to capture the image and get a print of that. So once you are into this ANSYS APDL launcher interface, the very first and foremost step is go to the preference and set which type of analysis you are trying to do. We are going to structure analysis, so we are selecting as structure analysis, pressing on OK. Moving on to the next step, that is the preprocessor. Therein, as you can see, the points are listed, and as per that only we have to do our analysis. So we will select the element first. As I told you, this is a beam, so we will select beam element, and as our element have two nodes, we will select two node beam element, press on OK. If you want 2-3 elements, press on apply. See here, this will come, right? If you want more, apply, cancel. We want only one element because we have a beam given with same material and same properties. Therefore, we'll delete one. So we are left with only one. If you want change that, you can go to the option and do whatever changes we need here, right? Okay, then close. One element is added. Now, as circular cross section, as circular section area is not given, sorry, the cross section area is not given in the problem. It is instead said that it is moment of inertia. So instead of going for real constant, we will go to the sections. So if you either we have to go for real constant or for sections. But now as it is a beam element, in case of a beam element, you have to always go to the sections. You don't have to consider the real constants. So we will go step by step. So we will go first the material props. There we will select material models, and if you can see the question, only one material is given to you. Therefore, we will select that property of that one material which is given to us. So the property given is 200 e raised to 9 and the bulk modulus is 0.3. And if suppose there are more materials if you want to add, you can add here new material, name of the material, and keep on adding. If you don't want it, press right click and delete it. So we have only one material and one element. Now going to the section, we see the section we have considered as square section. Go to common sections. Once you are into the common section, write the ID of the section, name of the section. You can write square, any name you can give, section 1, section 2, section 3. Let the offset be at the center, and as we have calculated, it is 0.13 meter and h also 0.13 meter. So we will apply it. Here you have to apply it, else and otherwise it won't be available when you are connecting the element. Press on OK. So you have entered one section of the beam. As there is only one section given to you, we will select only one section. If it would have been a stepped bar or a step beam, then there would have been different sections. Then you have to select different sections. Sorry. Once the section is completed, we will go to modeling, create the nodes. Before creating the nodes, you see what are the coordinates for node number 1, node number 2, and node number 3. If you can see, node number 1 is having coordinates 0, 0, 0. Node number 2 is having 5, 0, 0. Node number 3 is having 10, 0, 0. So we will make the nodes in active screen. So node number 1 having properties 0, 0, and 0. Press on apply if you want to add more. So I am pressing on apply because I want 2 more nodes. 2 having 500, press on apply, that is 3. Now it is having 10 zeros. Now press on OK. If you want to add more nodes, then press on apply. If you want to end it, you need to press on OK. So these are the 3 nodes which we have. Now going to the elements. Before going to the element, as we always do, we select the element attribute. But if you go into the element attribute, see, one element, one material, and no real constant is not defined, and only one section is defined. So press on OK because everything is having same material, same property, and same element. Then connect the nodes through element. Connect the nodes to form element. See, I have selected this, so count is 1. Again, I will select point number 2, count is 2, and element node number is 2. Press on OK. So here I have got my first element. Now going on to the second element, find this and this. So count is 2, nodes are 3. Okay. So this is the creation of nodes and elements. Moving on, we need to define the constraints, or you can say boundary conditions. So we'll go to the loads and define loads. Go to apply, and apply, go to structural, and in the first point of the structural, it it is displacement. Displacement on the node. So a displacement on node number 1, we will press on OK, we'll get one screen where we need to define. So all degree of freedom on node number 1 is 0 as it is fixed. If it is fixed, there won't be any displacement on X direction, Y direction, Z direction, no rotation, nothing is there. So okay, so now if you can see on the symbol, it is fixed on both the side, it is fixed. Now on displacement on nodes, node number 3, you press on OK, and if you remember, I told you node number 3 is having a roller support. The roller support is having it can have a displacement in X direction, in Z direction, it can also rotate. It is only fixed in the Y direction. So in Y direction, we are putting the value of displacement as 0 and pressing OK to get this as your roller support over here. So this is like on the 1, it is fixed. At point number 3, it is having a roller support. So now point 1 and 3 is taken care of. Now we need to define the load and apply the load on the node number 2, right? So we need to go to force and moment on node number 2, select the node number 2, press on OK. We need to apply the load in Y direction, that is negative 20 kilonewton. Okay, so you press on OK. So this is fixed. There is load on node number 2, and again it is roller on point number 3. If you want to check what all you have done, go to list, go to nodes. You will come to know what are your nodes, how many nodes are there, what are the coordinates of the node, if there is any rotation given. So these are the coordinates 0, 0, 0, 5, 0, 0, 10, 0. So this is correct. Now if we want to check the elements, we can go to elements, attribute and real constant. Element number 1, material property 1, type 1, real constant, section is 1. So element number 2 also the same property. Okay. Now if you want to check with the load or the displacement, go to load, constraint on all nodes. These are the constraints. Node number 1 is having 0 displacement in all the degree of freedom, it is restricted. And node number 3 is restricted in Y direction. So this is the restriction. Now if you want to see loads, forces on all nodes, you can check at node 2 in Y direction, it is having minus 20,000 Newton force, right? So this is all checked. Once we are done, satisfied with the checking, we can go to solution, press on the solve and current ls, solve current ls, solution is done, press on close. Once the solution is done, we can check with our results, go to general post processor, we can check the result using a plot control or a list. So plot result, we will first see deformed, undeformed shape. So this is the white black line is your undeformed shape and this is your deformed shape, right? So if you want to see in 3D, you can see in 3D, this is your deformed shape. If you want to change it to 3D, go to plot control, style, size and shape, and display of elements you on. So these are your elements. Now you can rotate this in any direction and see. You can rotate in this direction. These are your results in form of plot. So this was the shape of the element before displacement. This is the shape of the element after displacement. If you want to save your work, you can go to capture image, go to file, save as, and on the element, on the directory which you have set, you can go there and save your file. Right. Once it is saved, if you want another results, go to control plot, nodal solution. You can have nodal solution in X direction, Y direction, Z direction. So these are your nodal values of displacement in Y direction. You can again capture this image, save in that directory where you want to save it for future use. You can name it any name you can give. So this is all about your nodal solution. You can also check with your element solution if you want. We can see the list results. These are nodal solution. Here we can see the result in form of list. So if you want to see detailed summary, you can see detailed summary. If you want to see iteration summary, you can see iteration summary. If you want to see percentage error, you can go in some of the thing. You can see it. Go for nodal solution, degree of freedom in y direction. These are your displacement in case of y direction. Again, if you want to save it, you can save it. Save in your file. This is for your future reference or also to show your examiner how what are your results. Again, if you want to check with some stresses, you can check with your stresses in x direction or y direction, right? The form of the lot result or list. Again, you can go to reactions if you want. All item present. These are your reactions at node 1 and node 3. Since your node 1 is fixed, it will have some reaction in directions which are fixed. So in y direction, it is having some reaction, and in case of moment, it is having some reaction. Again, you can save this file if you want. Name it anything you want. Save. So this is all about how we can proceed for analysis of